I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the student and our students who might be watching this later. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so factor modules. So we are, man, some of these markers are really, really stuck on there, you know? See, I think I've got you where I want you. Not entirely. Let's see here. There.
It's okay. Maybe a little to my right, whenever you get a chance. So the corners, yeah. The corners are matched up.
Okay. All right, so we are now in section 7.4 of Erdmann and Wilden. This is on submodules and factor modules. My goal today is to at least say some intelligent things about the SL2C representation stuff. We'll see if that's crazy or not. So, all right, so here he goes. He says, suppose that V is a Lie module for the Lie algebra L. A submodule of V is a subspace W of V, which is invariant under the action of L. So let's see here. I guess, rats. I need to remind us what is a Lie algebra module, right? So you have something like L cross V goes to V, and we're talking about a pair of X comma V, and our typical notation is X dot V for the action of X on V, and it satisfies various axioms. I'll write down this one. For instance, if we have X comma Y, the bracket of X and Y acting on V, we kind of get a commutator of sorts of the action, right? We get X dot Y dot V minus Y dot parentheses X dot V. All right, so that's a Lie module L. All right. And then we talked about
Acting on L.
Lie module is all of this together, but sometimes we'll just say the module is V, you know. And then
I was thinking that like it was like a Lie group acting, or a group acting on a Lie algebra.
a Lie group acting on a Lie algebra, no.
No, not a Lie, just like a group, because that's what we define modules as back like when I
Oh.
abstract algebra 2.
Yeah, for us, so the module in that context is a
The group action.
well, I think it was, yeah, that's true, but you know, like essentially you could think of it as a vector space over a ring, right? So this is kind of like a vector space over a Lie algebra. That's not quite right. Well, is it that? I guess it's that. I mean, you got a way of multiplying the algebra elements on the vector space, right? So, and then there are two different ways to describe. You could also write it in terms of, sorry, I lost my place here. So, we can also talk about Lie algebra representation, right? And then given, what's a Lie algebra representation? Phi from L to GLV, a Lie algebra representation, which means it's a, what is it? It's a homomorphism, right? From L to the linear transformations on V, and it's bracket preserving, right? So the key feature being that phi of X bracket Y is equal to phi of X comma phi of Y, like that, right? But this is the commutator under composition bracket, right? Like this is explicitly phi of x composed with phi of y minus phi of y composed with phi of x over there. Those are operators. And anyway, so if you have a Lie algebra representation in that sense, you can make it an L module. You induce L module how? By x dot v equal to phi of x acting on v, right? We talked about this last time. All right. Okay, so given all that, we can then talk about submodules. Well, a submodule of V is subspace W of V that's invariant under the action of L, such that, you know, x dot W is an element of W for all x in the Lie algebra and W in the subspace. And you can also call this a subrepresentation. In this context, all right? Let me write down his examples. So let's see here what we got. So example 1, which is his example 7.4, is like L Lie algebra. Make it into an L module by the adjoint representation. So how does that work? Add add goes from L to GLL according to the rule what? The adjoint of X is an element of GLL. How is it defined? Well, the adjoint of X acting on Y is precisely the bracket of X and Y, right? So that gives you a Lie algebra representation, right? Okay, so in this context, what would a submodule of, what would it take to be a submodule in this context is the question we should ask, right? That's the point of this example. Am I, oh, for a second I thought my laptop had died. We're okay. I got the screen turned way down so I can't see you unless I get right in front of you, you know?
Well, we would just need a fee, right?
Well, we need W, a subspace of L, right? Such that, you know, oh, yeah, okay, so here, what's the adjoint? So here we have x dot y equal to add of x, y, I guess here. So we need x dot w, which is equal to, as it happens, the bracket of x and w. We need that to be an element of w for all x in L, right?
Yeah, I lost you on the right edge.
What is that? Well, in other words, W is a what?
Is it like an ideal?
Yep. So the subrepresentations of the adjoint representation are just the, you know, ideals. All right, so there's an exercise about this, which I guess I probably just did. Oops. Example 2. He's like, let L equal to B and F. Right, the Lie algebra of upper triangular n by n matrices. Right, and let V be the natural L module. In other words, let V equal to Fn, right? And so what's the action of L here then? So if we do, x dot V, it's just equal to xv, right? For all, x in Bn and V in Fn. This is matrix multiplication, right?
Yes.
Okay, he says take the standard basis of Fn and okay, so every example in this section is an advertisement for doing a homework problem, He's like, form W sub R is equal to the span of E1, E2, ER, right? Then you can show that this is a sub, an L submodule of Fn. So basically, take the span of the first so many standard basis things. And then, of course, if you think about multiplying a triangular matrix on things like this, you're going to, again, get things like this because you're dealing with an upper triangular matrix. It's pretty apparent that that works. So, all right. What is next? Well, example 3. He says, let L be a complex solvable Lie algebra, and suppose that you have a representation. So L, complex solvable Lie algebra. Phi, suppose you have a representation. Not saying what it is, just saying suppose you got one. And he says, since phi is a homomorphism, the image of phi is a solvable subalgebra of GLV. All right. So what you gonna do with it, Mr. Book? He says proposition 6.6, also known as the main step in the proof of Lie's theorem, implies that V has a one-dimensional subrepresentation. Man, these examples go from like mind-numbingly obvious to like, huh? In no time flat,
No, I think we showed that the solvable subalgebra thing was true.
Well, yeah, that I'm on board with that, but
well, proposition 6.6 is let V be a non-zero complex vector space. Suppose that L is solvable Lie subalgebra of GLV. Then there is some non-zero V in V, which is simultaneously an eigenvector for all x in L.
oh, okay. So V naught equal to 0, such that like a V naught is equal to lambda V naught. Well, I should say lambda of A, right? V naught for all A in L, right? Does that seem right to you? There's a common eigenvector. So he's claiming that that gives us a one-dimensional representation. Is that right?
Yes. Yeah, and more specifically,
Oh, okay, I get it. I get it now. I can explain. I understand now. So you have L is a Lie algebra, right? And L is solvable, right? But that doesn't help you. You know, you have GLV. Well, these are linear transformations on V. Okay. But image of phi is a subset of GLV, which is solvable. So I apply the proposition 6.6 to the image of phi, which is solvable. I get a common eigenvector in V, right? For which A V naught is equal to lambda of A V naught for all A in the, this is not in L, this is A in where? In the image of phi. Image of phi, right? So, okay, so I think then, how's it work? Well, x dot, I guess it's x dot v is equal to, phi of x acting on v. But that's equal to lambda of phi of x acting on v, because in here v is an element of the span of v naught, which is a one-dimensional subspace of v. I think that's what's going on here. Is you're the image under the given homomorphism gives you a something in the image of phi. And that, by proposition 6.6, how does it act on the eigenvector v? Well, by multiplication by the eigenvalue for that thing, right? Okay, yeah, fine. All right. So, continuing here. He says, suppose that W is a submodule of the L module V. We can give the quotient vector space V mod W the structure of an L module as follows. Oof. I'm going to erase the upper half of the board there, Audric. Is that okay?
yeah.
Oof. The tiredness is coming faster than I thought. It's not good. Do, 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 do. All right. So V mod W, what's that? Here you're looking at like x plus w, such that x is an element of V, right? It's the set of cosets of W, right? And he says you can define the structure of an L module as follows. You do x dot x plus, V plus W. How does it work? It's x dot V plus W. And this is called the quotient or factor module, right? And how do we prove that this is an honest to goodness L module? What's the first thing you want to check? All right. So,
Yeah.
we got that.
And then you want to track that the mapping is a bracket.
Right. Well, there's something more basic we need to check here. Since we're defining it on a representative, we need to check that it's independent of our choice of representative, right? So like,
Oh, it's independent of representative, yeah.
yeah, so like, suppose V plus W equals to V prime plus W, we should look at like X dot V prime plus W, right? Now here, that means that V prime, means V prime is equal to V plus some little W, right? That's what it means. The difference of them is in W. All right, and all right, so definition, this is X dot V prime plus W, right? But that's X dot V plus W, right? Which is X dot V plus X dot W by the module, by the properties of the module action, the algebra action. Then what? We have to assume something about W for this whole construction. What are we assuming?
W is just not space.
Right, yeah, exactly. We assume W is a subrepresentation. In other words, that X dot W is an element of W again for all X in L and W, right? That was what our definition of subrepresentation. So given that, this right here is an element of W again, right? Which means that this is equal to X dot V plus W, which of course is X dot V plus W, which proves that the action on the factor module is independent of our choice of representative. So and once you have that settled, then you can go and you can check the needed axioms for the module action, right? Like there were the linearity in the first, linearity in the second, and then, like you said, the preservation of the bracket through the, we can look at the bracket. Oof. Or was I, I'll move you. Is that good?
Yeah, I can see for about half the board, yeah.
Okay. So let's see here. By definition, this is xy dot v plus w, right? And then by the definition of, since this is an L module action, we have that's x dot y dot v minus y dot x dot v plus w, right?
Yes.
But that is Sorry, I'm struggling with notation here. X dot son of a gun. X dot y stink. Well, it's x dot y dot v plus w minus y dot x dot v plus w. I mean, that's just definition of module subtraction. And then we're looking at x dot, oh man, Audric, I'm sorry.
I think you just have to show that the y and v and x and v are both w.
Well, I'm trying to think about what I need to show. I'm supposed to show module action, axiom M3 on page 56, yeah? Or if you like, the axiom M3 on page 55. But what does that look like in our current context is what I'm struggling with. Yeah.
So, well, for one, we have if you did this out, this would be what? This would be y. What would this be? This would be bracket. This is left side, so it'd be bracket xy dot b.
Oh,
right?
oh, I'm very, without Jacob here, it's dangerous. Because while I have moved you in the computer, I never moved you in the camera. I have to remember to do that. There we go, though. I got it now. Sorry about that. Yeah, I mean, yeah, this is right. This is x dot y dot parentheses v plus w, right? Yeah. Minus y dot parentheses x dot parentheses v plus w. And then that's what we're trying to prove. Yeah, I mean, because let's call this v bar. X comma y dot v bar is equal to x dot y dot v bar minus y dot x dot v bar with parentheses, of course. I mean, this is M3, right? Where v bar is the element of the vector space we're looking at, which in this context is a quotient space. So it's like, this is what we're trying to prove for M3, and this actually is it. I couldn't see it a minute ago. Brain not working. So, does that make sense, or I hope it makes sense. All right, so let's go on here, and Whew. So his next example, example 7.7, let me move you. He says, suppose you have, is that good? Is that good, Audric? Yeah. Okay. Suppose you got an ideal of a Lie algebra L. We've seen that I is a submodule of L when L is considered as an L module via the adjoint representation. So now he wants to circle back and talk about the factor module. All right, so I an ideal of L, right? Then factor module L mod I, right? How's it go? X dot y plus I is, of course, okay, so we're talking about the adjoint, right? So here we're talking about adjoint of X acting on Y plus I, which of course is explicitly the bracket of XY plus I. Ooh, AKA L mod I is Lie algebra with bracket. If we take the bracket of X plus I with a Y plus I, what do? We just bracket the representatives. He says, so regarded as an L mod I module, the factor module L mod I is the adjoint representation of Li on itself. The factor module L mod I is the adjoint representation of L mod I on itself. Interesting. And let's see here, his next example, he again looks at upper triangular matrices and column, n by n column, n column vectors, and looks at the W sub r, well, he calls it V sub r actually, that we defined earlier. So he looks at the matrix that would act on the quotient space. Well, anyway, you can explicitly look at the how to say it. Well, I've erased that thing. All right, fine. The next example is not difficult, I'm just tired. So if you're, all right, example 7.8, he's letting L be the, Bn, excuse me, B sub n, rather Bn comma F, the upper triangular, and he's letting W equal to V sub r, which is the span of E1, right, all the way out to ER. And we argued before that that was a submodule, right? So since that's a submodule, we can look at L mod. We can look at here. So here, this was a V equals to Fn module, right? So and the module action is just given by the natural matrix multiplication of upper triangular matrices by n column vectors, right? Okay, great. So if you look at V mod W, well, that of course is, things of the form x plus W. And so if you want, what's the dimension of such a quotient space? Can you tell me, Audric? I'm modding. Yeah.
Such a quotient space.
Yeah. What's the dimension?
Wouldn't it just be like you just subtracted the 2 dimensions, right? It'd be so 1-dimensional less.
Well, not 2 dimensions here. This is r-dimensional, right? I mean,
In what sense?
in the sense of vector space.
Oh, okay.
In sense of f vector spaces.
Yeah, the basis, but yeah.
So that's the thing we're squashing to 0 in this construction, right? So the dimension of V by W is actually n minus r. All right? And in fact, the basis for this would just be what? There's a natural basis here. It's just the span of, let's say, EJ plus W such that J equals to R plus 1, R plus 2, all the way out to N. Notice that there's N minus R of these. Consistent with my claim that the dimension of the quotient space is N minus R. So the natural question to ask here is, what is the factor module? What's the factor module action on the quotient space? Like, how do we understand it in terms of a calculational basis? Like, what is it? In the previous example, we saw that the factor module is just literally, given by this formula here. So, if I have an upper triangular matrix, right?
Are you on the other one, or you're on the camera?
Oh, I'm sorry. I'm just here. I'm right here, hiding in plain sight. So if you got, if you've got a B in L, and you look at, B dotted with, acting on X plus W, how's that go? I mean, it's literally Bx, right, plus W. But of course, you can just think of that X. You can absorb all of the, we can write any X here as equal to like X sub 0 plus X sub 1, let's say, where X0 is an element of F R and X1 is an element of F n minus R, like that. And because the and so I guess I could write B in blocks, yeah, like B1, B2, B3, B4, like that, something like that. Blocks, to quote my linear algebra professor, Dr. Hartwig. And what happens, of course, is that we can set, I mean, in this context, we can just set x not equal to 0, right? Because we can assume that our representative has the, just throw away the part that's non-trivial in W, right? We can absorb the W piece. So I can just put x not equal to 0, essentially. And so what I've got, you know, is like, well, B2x1 and B4x1 plus W. So the whatever's in the first, essentially whatever's in the first, using block multiplication here. Whatever's in the first and the third blocks there of the original B, it don't matter. Like the action of the matrix on the quotient is completely governed by blocks 2 and 4, which correspond to the last n minus r fold columns of this upper triangular matrix. And I'm thinking that what the book has written is another notation to express this same well, what do you want to say? Feeling? Claim? What's he got here? It's obtained by taking the lower right and, oh, right. And actually, and I'm still not being greedy enough, Audric, because remember, we're dealing with this W module. So this we can just as well replace with 0, B4, x1 plus W, right? So actually, in the final analysis of things, only this block, the lower right r by n minus r by n minus r block of B is what matters to the action. Well, let's say the induced action of the upper triangular matrices on the the quotient module here. And that is what he says in the book, in a different notation, but yeah. All right, so that brings us to section 7.5. Let's see here. He says the Lie module V is said to be irreducible or simple if it's non-zero and it has no submodules other than 0 and V. Let me write that down. Where shall I write it? I guess I can erase that, yeah. Somebody texted me. What's going on here? Am I going to the game tonight? What do you think, Audric? Should I go to the game?
Is it your son's?
Yep.
Yeah, probably.
Yeah, I think the answer to that is yes. It starts at 6. We're good. All right. So, let's see here, where was I? What does it mean for, come on, definition, Lie module V is irreducible or simple if V is not equal to 0 and has no submodules except what? 0 and itself, right? You can't avoid those, right? Every vector space has the 0 space and you know, it's itself as subspaces, and of course those are going to satisfy the satisfy the criteria for L module. The V is an L module, so that's unavoidable, right? So he says, suppose that V is a non-zero L module. We may find an irreducible submodule S of V by taking any non-zero submodule of V of minimal dimension. If V is irreducible, we just take V itself. The quotient module V by S is will have an irreducible submodule S prime, and so on. In a sense, V is made up of simple modules S, S prime, dot, 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 dot. One says the irreducible modules are the building blocks of all finite dimensional modules. Let's see if we can. I think we'll understand it with the. We should understand it with the examples which are upcoming. So the idea is, all right. Let's think about this. We've got a V module. Excuse me. We had an L module V, right? So if it's if it is already irreducible, then great. V is the sum of an irreducible module, right? But let's see here. So if V is not equal to 0 is an L module, then let W not equal to 0 be of minimal dimension. Right? So again, this is in submodule. And he doesn't call it. He calls it W equal to S. Sorry, so I'll stick with his notation for the sake of understanding the discussion, right? So he says. What? I'm sorry. He says the quotient module V mod S will have itself have an irreducible module S prime, and so on. All right. Okay, fine. Let's go on here. So, all right, fine. V mod S is L module, right? I'm going to go on to his examples. There's something I'm missing here, Roderick. I'm sorry.
Okay.
I mean, so number one, V is one-dimensional. then V is irreducible. That's just kind of like linear algebra, right? Like, if you're one-dimensional, the only subspaces you have are yourself or 0, right? So obviously it's irreducible. Number 2, if L is a simple Lie algebra, then L viewed as an L module with respect to the what? The adjoint action, right? We can make any Lie algebra module with respect to itself using the adjoint action. And if we do that, it's irreducible Lie. So now we need to remember what did we mean by simple Lie algebra? Do you remember?
Simple Lie algebras. Let's see.
Right, there does not exist a, like it's got no idea. Okay.
Just non-abelian?
Not an abelian, but it has no non-trivial proper ideal. So a simple algebra is one where the only the only ideals of the algebra are 0 or itself. And I don't know if we allowed 0 to be an ideal. I can't remember. We might have. And remember, so for the adjoint action, what are the sub-representations? As we were talking about earlier today, the sub-representations of the adjoint action are the ideals of the subalgebra, right? So if you have a simple algebra, you have no sub-representations for the adjoint action. So what this tells us is that L is irreducible as an L module with respect to adjoint, representation. And of course, that's that's why that's the reason for the terminology simple is somewhat tied into this, example here as well. We call things simple if they can't be broken down, right? So,
Except primes.
yeah, they're like primes, right? Let's see here. Why don't we call primes simple? That's good. Find the simple factors of the number. We should say that, right? You should.
Yeah.
We should change the terminology. We're like, no, we don't talk about primes anymore. They're simple numbers. There you go. He says, for example, SL2C is irreducible as an SL2C module. SL2C is irreducible as SL2C module. If L is a complex solvable Lie algebra, it follows that all of the irreducible representations of L are one-dimensional. Why is that? I mean, this is built over the back of the example we did half hour ago. You know, where we,
Why is it irreducible model?
you know, why are they necessarily one-dimensional?
Because
I probably have to write the details of that example out again, you know. Let's see here, so,
complex solvable. Is it because there's no non-trivial ideals? Are you talking about?
it was the, we had, you know, image, if we have phi from L,
Because like must be one.
maybe, let's see here, our phi goes from L to GLV, representation, M phi, solvable sub algebra of GLV, right? And V has a one-dimensional sub-representation. Proposition 6.6. V has one-dimensional subrep. Okay, so yeah, I mean, it's really just counting. I mean, if you just think about what's going on here, it becomes obvious, Audric, because what the earlier example said is any representation, right? Any representation of a solvable Lie algebra, right? Complex solvable Lie algebra has a what? Has a one-dimensional sub-representation, right? In other words, it's not simple, right? It's not irreducible because it has a sub-representation. How can you the only way to avoid it then is for it to be a one-dimensional representation. If it's a one-dimensional representation, then we're back into case one up here, and we avoid the inevitable existence of a sub-representation, which is not the representation. So, So, yeah, all right. Okay, move on. Move along here. Let's see here. And then he has an exercise, which is probably worth doing. Most of the exercises in this book are worth doing, right? So, let's see here. Another criterion that's sometimes useful is given in exercise 7.13. Oh, here, exercise 7.3 has a criteria to check for irreducibility according to a particular formula. All right, let me go on here. So if V is an L module such that V is equal to U direct sum W, where U and W are both submodules V, then it's said to be the direct sum of the L module U and W. All right, this is what I was looking for, Audric. When this discussion feels incomplete to me without the following discussion, all right? So here it is.